Okay, and I am not sharing my screen anymore. I should be sharing my screen. Okay. Now, whoops, what is that? Starting for real. Okay. Yes, good morning again. So we're now in the topic 9 folder. Last topic, the topic 8 of Python SQL. Very fast, just the 1 day, half day sort of overview of the homework assignment that is again not due today, but due this coming Thursday. And because we have the homework assignment due this coming Thursday, I've decided that we won't have a quiz this Thursday, and we'll have it next week instead. So the only things going on this week are your homework assignment and the lab. High-level idea of what we'll be talking about today, this idea of MVCC, multi-version concurrency control. This is how Postgres, under the hood, is implementing all this transactions and locks and things that we've been talking about, and things that are important for your upcoming homework assignments and inserting into the database. But before we do that, a few quick announcements. First announcement is next Monday, I'll be giving a presentation that you're all invited to in the Freeburg Forum from 12:20 to 1 about being at the NSA and North Korea. One maybe fun thing about that. So I used to work on nuclear submarines. I will bring with me some tritium to Freeburg Forum. Tritium is one of the things inside of nuclear warheads that makes them thermonuclear instead of regular nuclear. They go right in this little pit inside in between the uranium-238. It glows in the dark, so you can see that glow in the dark if you would like. And also, I've worked recently getting cell phone infrastructure in North Korea, improving that. So I might talk about that as well. More class-oriented announcement. If you are, so on GitHub, I haven't done this previously, but there's this issue up here that's been pinned up here. If you're getting errors on your assignment, that only happen on GitHub and not on the Lambda server, this issue up here will have instructions or a description of what's going on and how to fix that. So I've pinned, this is an issue from a previous semester, I've pinned that to the top here so you can all see that. Two other announcements. There's a new extra credit opportunity posted. This extra credit is a game, Deadlock Empire, right here. It's about managing concurrency, so the stuff that we'd previously been talking about. In this case, the game deals with C#, so obviously different than the languages we're using in class here, but all the concepts are the same. And it's also just useful in general to get exposed to more programming languages, so that's why I'm giving you this game as an extra credit. The structure of the game, there's just a bunch of sort of different levels that you walk through, and as you beat one level, you get to go on to the next ones. If you get up to complete the locks over here, you'll get 1 point of extra credit. The locks at this point goes through everything that like deadlocks and the different locks conflicting with each other. So very related to the stuff that we were talking about. The stuff beyond that goes into alternative methods of concurrency control that is not used in SQL standardly. And but if you would like to complete those, you'll get an additional point of extra credit as well. So maximum 2 points of extra credit from this game if you would like to do it. Last announcement here. Over the weekend, there has been some very entertaining, from my perspective, drama related to security on the internet and this library called XZ. And so I just wanted to give an overview of what's been going on here. In particular, so this XZ libraries had a very major security vulnerability found inside of it. And this is a standard library that's installed in almost all like Linux and Mac machines. So those of you who have Macs, you probably have this library installed and are potentially vulnerable to what's going on here. You might not have heard of the XZ compression format before, but it's used widely, like internally, in a lot of programs. One of those programs is OpenSSH. So that is when you connect on SSH to the Lambda server, OpenSSH is the daemon running in the background on the Lambda server that you're connecting to. So the Lambda server using the XZ library as a concrete example. This security vulnerability was discovered by a Postgres developer, somebody working at Microsoft on Postgres. Again, even though Microsoft has their own SQL Server product and their own operating system Windows, whenever they actually care about their data, they run Linux as their operating system with Postgres as their database. And so Microsoft is one of the actually biggest employers of Linux developers and Postgres developers. And this Postgres developer noticed that his OpenSSH connections were going like unbelievably slow at 20 milliseconds instead of just 1 millisecond. And that led him down a debugging trail that resulted in him tracing that performance degradation back to the XZ library. And in particular, the XZ library had a special trigger inside of it that when it noticed that OpenSSH was the program that was using it, it did a whole bunch of stuff in the background that enabled a backdoor that allowed anybody to connect to SSH without knowing the usernames and passwords of that particular machine. So if there are many OpenSSH systems in the wild right now that are vulnerable to this, and so it's possible right now for anybody to connect to those systems without knowing the username and password. A little bit more background on the XZ library. So XZ first created in 2005. The last 20 years almost only maintained by this one random person, Last Colin. And before this weekend, basically nobody in the world knew who he was, but he was one of the people who modern infrastructure was built on. Again, basically all computers in the world, Linux and Mac machines, having this library installed on them. And then in 2021, this random new volunteer, Gia Tan, arrived and started contributing, and most of his contributions were real. I don't know, you can look, a lot of people have gone through the actual Git repos, looking at the history. There's thousands of commits, most of them doing very important things, but some of those commits doing the bad things of adding the backdoor, and so it's this person who's responsible for the backdoor and not Last. The particular backdoor, again, is a very, very sophisticated thing that's been added. Most people consider us very lucky that this random Postgres developer happened to notice this 19 millisecond slowdown, something that very few people would notice. And this is the only way that we knew that this backdoor was added, and that all of the systems, many systems in the world, were compromised. So at the beginning of the semester, I sort of complained, maybe you all complained too, that you had to do this extra VPN step of logging into the Lambda server. But this is the sort of reason about why you have to do that, is because if the Lambda server was not behind the VPN, then it would have been open to this attack. Anybody in the world could have connected to it without knowing any usernames, password, done whatever they wanted to the machine. But because it's behind the VPN, it's much harder for random people to do that. So fun, kind of security aside, relevant internet drama that matches up with a lot of things we've been talking about in class here. One last fun picture. This is so XKCD, if you haven't seen it before, common web programming comic. This is one of their most famous comics where you have this all random, like modern digital infrastructure on computers. And there are, in this case, the picture only has this one little block here supporting everything. But there's really thousands of these little blocks maintained by just like one random person, like Lass Collins, who nobody's ever heard of. And if something happens to that person, they get compromised somehow, then all of modern infrastructure comes crumbling down. One of my favorite things about this story is that Lass Collins happened to be on vacation over the weekend, and he has told everybody that he is not going to help with this problem because he is on vacation and nobody is paying him to help with this problem. So I have a lot of respect for him for that. Okay. Real material for today. So again, MVC, multi-version concurrency control. This is the technique that Postgres uses internally for implementing the atomic and the isolated transactions. So all the material on the past quizzes, we've seen like what it does. Now we're going to see how it does it. And understanding how it does it will probably help clarify some of the things about what it does. But more importantly, it's going to help us understand how to make our select queries fast. So again, I've been talking about this the whole semester. We're going to eventually get to how to make our select queries fast. This is sort of the last needed building block that we have. And then starting with next week, the next topics that we'll cover, it'll be just about actually making these select queries fast, going down from multiple hours down to milliseconds in runtime. There's a lot of material here that we'll see, but fortunately, it's all going to be much more straightforward, easier than the transactions locks material. Just what makes this section hard is that there's going to be a lot of things. Okay, so because there's going to be a lot of things, we are not going to cover everything in class, and there's going to be reading over here that you will be responsible for. So I've listed out these sections in particular of this link over here. This is a textbook that is a textbook for Postgres developers. The internals of Postgres textbook. This textbook, so I guess one of the other things that I like about the Postgres system is that a lot of unlike many other systems, Postgres is a very international project. You have people from Japan. This is a Japanese author working together with people from Russia, even though working together with people from the US, even though all of, for example, like Japanese and Americans have many problems with things that are happening in Russia right now at a political level. At the like individual level, we're still able to cooperate on these like important infrastructure projects that that the world depends on. Actually, after this section, the next section that we'll be looking at, the textbook from that will be written by a Russian who's still in Russia working on Postgres right now. Okay, so this is our textbook. There's a lot of material in this textbook. You'll basically be responsible for chapters 1, 2, and 5, and 6 over here. 1, 2, and 5, and 6, and nothing else. And today in class, we're going to go over at a high level all of the those sections. Probably not finish it on Thursday. One of the hard parts from a student's perspective about this section is that because there's so much material, it's hard to know exactly what you need to understand testing wise, like evaluation wise, as a student perspective, like what's going to be on the final exam sort of thing. And the answer for the final exam, again, it'll be an oral exam, is that everything in these 4 sections could be something that I ask you on the final exam. So definitely recommend that you spend the hour or 2 to read through all of these sections. But also to help you sort of focus your reading, and for quiz purposes, there's this questions.pdf file that you can use to focus your reading. This is what it looks like. It's a bunch of true-false questions. There's, again, just a lot of small details in these sections, and I don't really like the true-false questions. It's much more fun to do the more interesting style of questions that we had before, but there's just too much stuff to have that kind of question, so it's all going to be true-false for your next quiz. In class, we'll talk maybe about like sort of half of the material from this true-false question, so you could answer about half of this just from class material, but the other half is going to be stuff that you'd have to find in the textbook, reading it yourself. Okay. Any questions so far? Okay, then let's get into the textbook material. So each one of these chapters has like an introductory section and then a bunch of subsections. The introductory section you'll also want to read. Some of them are very small like this, but other ones have a lot of a couple pages long, more useful information. But the purpose of this first section, this first chapter, is just to give us like a big overview of what's going on inside of Postgres. And in the lectures, I'll be focusing on the different figures in this book and trying to explain to you what those figures are and why they're important. So this first figure right here is the overall structure of a Postgres database. And one of the, confusing things about Postgres is this word cluster inside of Postgres that a lot of, colloquially these days in like the 2020s, 2010s, clusters of computers has referred to many computers working together on like one problem. But in Postgres around since the 80s and 90s, cluster had a sort of different meaning back then, and in Postgres, a database cluster runs on just an individual machine, just one machine. So one cluster can have multiple databases inside of it, and that's why it's called a cluster. So confusing terminology there, but cluster refers just to one machine. The idea of having multiple databases inside of one database cluster is so that you could have, say, different programs, different applications running using one database. These days, with the development of Docker, that's not very common to do. You would typically only have one database inside of one database cluster because it's very easy to have multiple database clusters with Docker. But for historical reasons, Postgres has the support for multiple databases inside one database cluster. Okay, let's see, let me preload some of these tabs over here. This section 1.2, I'm not going to talk about this in too much detail, but this is all background information on where Postgres is storing the information on the hard drive, and all things that you'll need to be able to understand for the quiz and for completing the future assignments. So read 1.2, we're not going to talk about it in detail though. 1.3, this is the first section that's going to be super important for us to talk about in detail. And this is how, for an individual table, how does Postgres actually store the information for an individual table? We'll talk about how it does that and what the sort of performance consequences of that are. The first important sort of vocabulary concept here is this: what is a heap table? Every table that we've talked about so far in class is an example of a heap table. In Postgres, all tables are heap tables. So if you see the word heap in front of a table, it's exactly the same as a table. Heap just describes the sort of internal data structure that is being used to implement the table. The heap data structure here is different than the heap data structure you might have seen in CS46 or your data structures course. Not that kind of heap. It's, for, again, weird historical reasons, just happens to have the same name. In this kind of heap, we have one file is divided up into pages or blocks, and those pages are going to store the information about our database, the information in the table. So in this picture down here, zoom in a bit. On the right-hand side, we have a zoomed-in picture of one of our blocks inside of one heap table. And on the left-hand side, we have sort of a zoomed-out view of how those blocks or pages are related to each other. In the table file itself, there are these pages that are just sort of appended one after the other. So from 0, starting counting at 0, down to in over here. And each one of these pages is always exactly the same size, 8 kilobytes or 8,192 bytes. Inside of the individual page, there's some sort of header information at the top, shown up here in blue. And then the stuff in gray down here is the actual information of the tuples that is being stored. So in this case, this particular page has 2 tuples or 2 rows that have been added into this, this database. For the header information, for our purposes, we're not going to care about most of these things. The only ones that you'll care about are this PD lower and PD upper pieces of information here. What they are used for is for tracking where the tuple information is stored actually inside of the page. Again, so the gray information down here, the gray spots, that's the actual information, the data stored. The white information, this like big white space, that's free space, or also called a hole in the page. And this is the location, this is the information, this is the location where we can place new information when we do, for example, an insert into the table. It will get placed inside of this free space right here. The reason why we need to understand all of this like detailed internal structure is because we're going to need to understand exactly what Postgres is doing under the hood when we run a select statement so that we can understand why certain select statements are fast and slow. We'll need to understand what it's actually doing when it evaluates those select statements. So the first thing we need to understand is how does Postgres like get access to a particular row, to a particular tuple inside of one of these pages. And that's what these line pointers up here are referring to. So we have 2 line pointers up here, a 1 and a 2, and these point to the starting locations inside of the page of where the actual rows are going to start at. So the very first one over here, 1, points to the beginning of this tuple 1. And when Postgres says, okay, I need to access this tuple for whatever reason, in order to figure out where it is, it will first access this line pointer and then dereference that pointer, follow that pointer to this location, and read that information from here until the end of the page. For tuple 2, it will go from this location not until the end of the page, but until the start of the next tuple. So going from position 2 to position 1 will give us all the information inside of this tuple. Again, we talked maybe 3-ish weeks ago, like the last week before spring break, about what the contents of these tuples are. We saw that these tuples have their own like tuple header information, plus how that information is logically stored inside of Postgres. And so that's what each one of these tuple blocks is. One last sort of subtle point here is that, so this sort of 2-dimensional diagram is a common way for memory or disk space to be drawn out. But the way to understand what's going on here is that you start at the top left corner. So this is like position 0 right here. And then the positions move row-wise like you're reading from left to right. And then at the end over here, we go down 1 row, start again over here. And so this tuple 2, this information is actually contiguous inside of memory or inside of the hard drive, that this like ending spot of tuple 2 is somehow directly connected to this spot over here. It's just not drawn out in a single line for readability purposes. There's a lot of information that I'll be going over super fast today. So if you do have questions about something like not making sense, feel free to stop me and interrupt me, ask a question. But at this point, any questions about how this information is stored here inside of Postgres so far? Abhijit.
ahead and like access that unique ID row and then.
Yeah, so the question is, what exactly is these line pointers? There's not an equivalent concept in Python. There is in C. That's where the name comes from. A pointer here is the same as a pointer in C, if you've seen that before. But the idea is that this is just a number that's stored right here. In this case, it's going to be a 4-byte number, and it points to it has the byte offset. How many bytes do you have to travel from the beginning over here to where this particular tuple is going to begin at? So if, again, each of these numbers each of these pages is up to 8 kilobytes in size, then this number right here, referencing this last tuple, might be like 8,000, in which case tuple 1 here, the size would be 192 bytes, and then the line pointer here, the number might be 7,000, in which case tuple 2 starts at byte 7,000 and goes up to byte 8,000. The main thing that's important is that these numbers right here, these line pointers, are things that Postgres will have to inspect every time it's trying to find a tuple. And so it first finds the page, then finds the line pointer, then finds the tuple. Hopefully that's moderately helpful. Let's see, so that's the overall layout here. Again, the key vocabulary words, and then no more pictures on this one. This is next section, methods of reading and writing tuples. So we'll see like what are the steps that go on when we do one of these insertions, and how we that maybe will clarify what's going on, why this data is structured the way that it is. So here, in this figure right here on the right-hand side, this is the same figure that we had before. On the left-hand side, though, we have a figure that only has one tuple inside of it. And we're going to need to understand like what exactly happens when we insert another tuple or another row into the database, and in particular into this page of that particular table. So in this case, on the left-hand side, we only have one tuple, and so we only have one of these line pointers at this point, pointing to this location right here. The PD lower and the PD upper values, they tell Postgres how much free space is currently available inside of this page. So these red lines right here are somehow illustrating the values of PD lower and PD upper. PD lower, always the rightmost portion of these line pointers, and PD upper, always the leftmost portion of the actual data of what the tuples are. And so PD lower pointing here, PD upper pointing here, this one value, this line tuple, the only line pointer that we have pointing to the only tuple that we have in this database. When we do a insert into this page, the actual data of that tuple is added sort of from back to front. So starting here, tuple 1 doesn't get changed at all, but now tuple 2, that data is sort of prepended right before tuple 1. This new line pointer here is added, and the PD lower and PD upper values up here are then modified to, again, the PD lower always pointing to the very end of the line pointer section, and PD upper always pointing to the very beginning of the tuple section down here. And so PD lower and PD upper tell us how much free space is available in order to insert new tuples into this page. Again, like, why is all of this going to be important for us? Throughout the documentation that we'll be seeing in the next 2 weeks, all of these pieces of like this vocabulary will be coming up when you're talking about how to like do certain things to make a select statement faster. And we'll be talking about the PD lower and the PD upper values inside of pages, and you'll have to be able to understand what it's talking about in order to make your select queries faster. But this is the high-level idea of an insert and how that modifies the page storage. Yes, Henry?
So if there's ever a case where PD lower is bigger than PD upper, then that's going to, like, the insert statement's not going to work.
Yeah, so the question is, what happens if PD lower is greater than PD upper? And the answer is that if PD lower is greater than PD upper, then the line pointer up here information is somehow overlapping with the tuple information down here. And so that means the database has been corrupted somehow. So there are a number of tools inside of Postgres built in to like check, has the database been corrupted? One of the things that it checks, one of the invariants that it enforces, is that PD lower is always less than or equal to PD upper. And so when we are trying to insert new data, and for each one of these pages, we have to check if we were to add that new tuple inside of it, would that make PD lower greater than PD upper? If it would, then we can't insert that data into this page for whatever reason. And we'd have to pick another page to insert it into. Good question. Yes. Good question. The question is, what exactly is the meaning here of tuple? Tuple and row are synonyms of each other. For all of the purposes, all of our purposes in class, tuple and row are synonyms of each other. Some, like databases or theory people, would make very subtle distinctions about a tuple and a row, but you can think of them as being the same as each other in the same way that you can think of like a relation and a table as being synonyms of each other for our purposes. Good question. Okay, so this is the idea of writing into a database. We're now going to look at a high-level overview of reading these heap tuples, what's going on. There's two algorithms that this section gives a high-level overview of, the sequential scan and the B-tree index scan. We'll be covering both of these in gory detail later on next week, but this gives you just a high-level overview of what might be happening. So the sequential scan is sort of the most obvious thing that is going to happen here in your database if you have a select statement. And the idea is that we have, again, our table page, our table file is divided up into a series of pages, and we'll have to do a for loop over each of these pages in order to check each of every page that we see. We'll have to inspect, okay, there are 3 tuples in this page, and then go look at the values of each of those tuples and see if it matches whatever our condition is. So that's what this sort of diagram is illustrating, that you're going to touch every one of these tuples in a sequential scan, that it's basically just a for loop. The index scan is a little bit more complicated. This is the thing that we're going to be using, the main tool we'll be using in order to make our select queries fast. So we don't need to fully understand the details of this yet. Again, gory details next week. But the idea is that we're going to be using this alternative data structure, outside data structure called an index, which will tell us exactly where in the page file we can find whatever tuple we need to match whatever condition. And so in order to understand this index scan, in order to understand how to use indexes to make select queries fast, we'll need to understand this internal structure here. That's high-level overview of all of these section 1 parts. Chapter 2 here, this process architecture, this is all something that's, again, not going to go over in detail in class, but you'll have to understand it. There will probably be things here that so operating system concepts like shared memory that maybe are not 100% make sense to you, depending on your background. And my expectation is that you'll be able to read through this, and whatever terms don't make sense, you'll be able to look them up at least enough to be able to answer those quiz questions that we had, or that I provided for you. Memory architecture here, again, we're not going to go over it in detail, but you'll have to read through this in order to understand or be able to answer those quiz questions. The next section that we'll go on to in detail is section 5 over here about transactions. Let me zoom out for a second here. Chapter 5 is divided up into a number of sections here. The only sections that I'm requiring you to read for this course are 5.1, 2, and 3. This goes over the more details about how the inserting and updating works inside of Postgres. In particular, how it interacts with the concurrency control things, the locks and the transactions that we talked about last week. If you are at all interested in working with databases professionally, then I definitely recommend you also do 5.4 up to 5.7. That these are good material, things that you should know, but it's sort of not easy to evaluate students' knowledge on it. So that's why I'm not requiring you. I won't be testing you on 5.4 to 5.7. But I will be evaluating you. You are responsible. Everybody's responsible for 5.10, this maintenance processes here at the end. So 5.1 to 3 and 5.10 in this section. Okay. So high-level information about these sections. Transactions. Every transaction has what's called a transaction ID, and this is a 32-bit unsigned integer, and so that stores 4.2 billion possible values. And every transaction has to have a unique transaction ID, so there are at most 4.2 billion transactions that can happen inside of a Postgres database. That seems like a lot of transactions, and for many purposes, that is sufficient. But in like the big data sort of realm, again, like Instagram uses Postgres in their backend. Instagram is going to have about 4.2 billion transactions per day. And so there are a lot of subtleties here on this transaction ID related to how to reuse these transaction IDs for things. But the most important thing at this point is that every transaction has a transaction ID, and that is just a number. The section 5.2, this is going to talk about how that transaction ID is used while doing the insert, updates, and reads. And we're going to have to talk about the tuple structure in order to do that. So again, before spring break, we talked about the actual tuple structure here. We saw that there's this header information inside of every tuple. It was 23 bytes. And then there is this null bitmap, which for small rows, small tuples, is just going to be less than 1 byte. And so this overall non-data portion is going to be 24 bytes or less. But for very large columns, for rows with many columns, this null bitmap can be larger. And so this whole section over here could be 32 bytes. And then there's the user data. Last time we talked about this section, we did not, or this information, we did not go into detail about this heap tuple header data. This time, however, we will need to understand these 4 values over here, this txmin, txmax, tcid, and tctid information. This is the information that is stored inside of or the Postgres uses to determine whether different rows are visible to different transactions. And we will need to understand how, at a high level, it does that in order to understand, again, how to make the select queries faster. So these 4 pieces of information available for every row. You don't have to do anything special. They're always there. And you'll need to understand how they work in order to understand how to make select queries faster. Let's see. 5.3 goes into detail on the actual insert, deleting, and updating algorithms and what they do. So in class here, we'll walk through those algorithms and how it updates those 4 pieces of information. So in this first picture down here, we have our same page that we've been seeing before. There's 2 tuples already, tuple 1, tuple 2, these 2 line pointers up here in this header information. And here is a sort of expanded view inside of each of these tuple 1s and tuple 2s. So the user data here, very small amount of data, just an individual column, but we're really focusing in on this information over here. These 4 sort of, you can think about them as system columns, this auxiliary information that Postgres is tracking for us. When we do an insertion, so here we have an example of a transaction, a session that's happened where we begin our transaction, run some sort of insert statement, and then commit that transaction. This is creating for us our first tuple right here. And the insertion algorithm is relatively straightforward, that we have this txmin over here that gets set to whatever our current transaction ID is, and then 0, 0, and 0, 1. All 3 of these values always set to this sort of initial condition when you do an insert. Whenever you do a subsequent select query from your database, in order to determine whether this row right here, this piece of data is going to be visible to our Postgres session that is doing the select query, it will look at the xmin, the transaction minimum number, and xmax, the transaction maximum number that is visible to this query over here. So txmin over here, we have a 99. So any transaction numbers that are greater than 99 will be essentially have this, this information here visible to it. Yeah, I realize I'm going through this super fast and a lot of information, so probably a lot of questions going on, maybe not well formed enough yet to ask concrete questions, but anybody have a concrete question at this point? Okay, main takeaway, thing that you have to know about the insertion so far is that what it's going to do to these 4 headers over here, these 4 system columns, and the txmin gets set to our current transaction number. Everything else gets to an initialization value over here, which means that we basically haven't modified the data in any way. The deletion algorithm is maybe more complicated than you might initially expect, but makes sense that it has to have this complication after we've talked about the transactions, because you can't just immediately delete stuff from the hard drive, immediately delete stuff from the page. You can't do that, because if you did that, then future transactions or concurrent transactions would not be able to see that information when maybe they should. So what a deletion does, all that a deletion does, here we have on this box over here, we have another transaction going on with transaction ID 111. All that is happening inside of this transaction is deleting the rows from this database, from this table. And what all that deletion command does is it modifies this txmax value over here of 111. Puts in 111 because that is the current transaction ID. And so the intuition here is that the only transactions that are allowed to see whatever the value of this tuple was, the only transactions that are allowed to see this are those transactions which have a transaction ID between 100 and 111. All future transactions, all transactions that have a transaction ID bigger than 111 will not be able to see this information. And all transactions that have a value below 100, so a transaction that happened before the insertion happened, will not be able to see it. Only those transactions that happened between 100 and 111 will be able to see this piece of information right here. And again, the deletion does not modify this CID or this CTID in any way. In general, the insert and the delete, a little bit maybe awkward to understand what's going on, but once you've read through this, relatively straightforward. The update, more complicated. Logically, so logically meaning the way to think about what's going on, logically what happens is that Postgres will delete whatever the latest tuple is, whatever the tuple is that you're updating, and then insert a brand new tuple. So the update command never actually updates the actual row in place, never updates the user value, it never changes the user data. None of these commands, insert, update, or delete, will change the user data inside of the tuple. All they can possibly do is change these header columns over here, these system columns. And the update, in order to do it, in order to make an effective update, is going to delete this system column over here. So this first A, again, our transaction over here, what it's doing, update table, set data equals B. So this row right here, instead of having an A, we're changing that to a B. We're first essentially deleting this row. The way we delete it, again, is by changing the TX max to 100. And then we insert a new row with the data B right here. And in this case, again, when you insert, you're setting this TX min to be 100, and then the T max to be 0. 0 meaning that it has not yet been deleted or updated in any way. So the most important thing to understand about an update is that it is an insert followed by a delete. Okay, yeah, good question. Is it an insert followed by a delete or a delete followed by an insert? Logically, they both happen atomically at the same time, so it wouldn't really matter which order you do it in. Yeah, okay, good question. So we've talked sort of about like what this TX min and TX max are, but we haven't really talked about this TCID or this TCTID. And the question is, why did these two things over here change? Or in this, I guess for this first update, only the CTID changed, and for this second update, both the CID and the TCID are going to change. The question about why these things are changing is that the different values here are going to be needed for the index scans that we'll be talking about. But the question about just the mechanics of what happened here, again, when we do an insert, we always start with 0, 1 in our CTID. This tells us essentially that this is the first time this row has been inserted and it has never been modified. Then when we do the update, when we actually modify it, instead of only deleting it, we update this CTID here, this 0, 2. It used to be 0, 1, now it's updated to 0, 2, and this is going to tell Postgres in the future where to find the new information related to this row. So this 0, 2 is actually like an address, a place to look for the new version of this row. If in the future there is something that points to this tuple, then we will see that, okay, this tuple here is, we call it dead. It's not available anymore to our transaction because it's been deleted or updated. And in order to find the new information, the CTID will show us where that new information is. The exact format about that is something, we can talk about exactly what is the format of these TID. TID here stands for tuple identification. These numbers here on the left-hand side, this is the block number, the current page that the tuple is being inserted to. And the rightmost side over here, this 2, is the tuple ID inside of that page. So the reason this tuple over here had a 0, 1 as its tuple ID is because it was inserted into page 0, the very first page of our table, at location 1, the very first tuple location in that page. So there was previously no data anywhere in this table, so we're using page 0, the first page, tuple ID 1, the first tuple. Then here it's updated to 0, 2 because now it's the second tuple inside of this page, but it's still at page 0. These numbers over here, depending on what's happening inside the database, they could be essentially arbitrary. This is just a location about where the next tuple is located, where the updated information is at. The CID over here, this is the total number of commands that have happened inside of your transaction so far. So this transaction started count at 0. This is the command 0 right here, and then this is command 1 right here. So CID 1 right here for the second command. Not sure if that answered your question or not. Good questions. Other questions so far? Okay, let's move on to I want to show you this section 5.6 real quick. You're not super responsible for it, but it's useful just to skim to understand what's in here. That I've given you sort of like a high-level intuition so far about what the xmin and xmax are for, that a row is only visible if the current transaction is between xmin and xmax. The visibility rules, though, are actually significantly more complicated than that for various edge cases. And so this goes into, these sections have what are the actual like full if statements about how to check if something is visible or not visible. So again, you're not responsible for this section, but reading through this section might help understand the motivation for why the inserts and updates happen the way they do, because they'll maintain the correct visibility to maintain those asset guarantees. Okay, we're going to go into section 6 over here, this idea of vacuuming. Vacuuming is going to be something that is super important for large Postgres databases. So databases, say, terabytes in size or larger especially. And it's something that's sort of unique to how Postgres works. And again, doing vacuuming the correct way is something that is going to modify the efficiency of our select statements. And so in order to make select statements fast, you'll have to understand how vacuuming works. Here we go. So at a high level, what does a vacuum do? So here we have on the left-hand side a picture of our table. Again, these green boxes over here, this is sort of a zoomed out picture of the table file where we have, in this case, 3 different blocks, blocks 0 to 1 to 2. Again, each of these blocks or pages, block and page, are synonyms for each other, the same way tuple and row are synonyms, the same way table and relation are synonyms. Each one of these blocks over here, each one of these pages is always going to be 8 kilobytes in size. And so then we have a zoomed in version of one of these pages in this picture right here. This picture has so something different than we've seen before. We have 3 tuples now, where one of these tuples is labeled as a dead tuple. A dead tuple means that it is impossible to create a transaction that can possibly see this tuple. So the tuple has been deleted or it has been updated, and the transaction has been committed, and there are no concurrent transactions happening. That will result in a dead tuple. And these dead tuples are taking up space on the database. Again, the update and the delete commands will never actually delete things from a page. It would be unsafe to delete things from a page because that would break the ACID guarantees. So every database that has updates or deletes happening is going to have always some amount of dead tuples inside of it. The purpose of a vacuum, one of the purposes of a vacuum, is to delete these dead tuples. And here, so this left-hand side, this is the before the vacuum. You can see the dead tuple here. And then on the right-hand side, you can see there is, in fact, no dead tuple over here. So this frees up the space, this free space right here. This white area is now larger. There is now more space available for us to insert new tuples inside of here. For various, yes, Henry.
So it doesn't remove the two, like that ID that points to
Yes, good question. So here you notice that the tuples down here, 1, 2, 3, we removed the dead tuple 2, but this 2 over here, this is not removed. The line pointer is not removed, and that is, so this is not a sort of typo in the picture over here. The line pointer is in fact not removed, and this is has to be this way for, again, complicated internal reasons. So if you had many updates and deletes going on, even if you are, so one of the things that you must do in that situation is have regular vacuuming to free these dead tuples, and that will free up some space in your pages over here. But eventually your line pointers will continue to grow until they take up the entire page. So updates and deletes have potentially very subtle performance consequences. Again, first main thing is relating to these dead tuples sticking around, taking up space. But the more subtle, more very long-term sort of issue is these line pointers staying around, taking up additional space. The line pointer is only 4 bytes. The tuples on the order of 100 to 200 bytes probably. So the tuples definitely more important in terms of free space, but line pointers still taking up space. Good question. Any other questions so far? Okay, so one of the sorts of final exam type questions that we might talk about, or yeah, we'll take a pause from this discussion for a second in order to talk about the structure of the final exam a little bit in this. Again, it's a one-on-one. You'll come to my office and we'll talk about I'll ask you questions and you'll answer those questions. For those of you who are graduating this semester, we will be using the Pagilla or the Twitter databases as like our example database, and I'll be asking you questions about those databases. For those of you who are not graduating, you'll be writing your own database from scratch, and I'll be asking you questions about your own database from scratch. And one of the things that I might ask you is I might say we're working on the Pagilla program and Pagilla database. I might ask you or say that our program, for whatever reason, has done a lot of updates. And then I'll ask you to walk me through what are the performance consequences of those updates. And then you would be expected to then be able to talk about, well, I know that updates don't actually delete information from the pages. All they do is change this header values. That'll result in a lot of dead tuples. And then we'll need to be able to perform the vacuums at a regular interval to free up space related to those dead tuples. And so I might ask you to, for example, draw that out, and you would have to draw out a diagram that looks something like this, explaining the structure of these pages and how the vacuum actually removes those dead tuples. So again, we'll talk about that in more detail closer to the final exam time, but that is one of the ways that you'll be evaluated on this knowledge. Yes? Question is, can a tuple somehow come back from the dead? So it turns out that the idea of like zombie things coming back from the dead is very common in computer science processes. For example, you probably if you're running a Mac right now, you probably have several zombie processes on your system. Zombie processes also on Linux systems. Windows is not as fun, so they don't have zombies on their systems. In this case, though, these tuples will never come back from the dead in any way. That once it's dead, it has to be taken away and it can't come back. Okay. So stop our aside about the final exam here, go back to the material, and we'll finish up here about vacuuming. So this is an ordinary vacuum. An ordinary vacuum, all it does is remove tuples, remove dead tuples happening on like a page-by-page basis. The next type of vacuum is is a full vacuum. So this section 6.6 right here talks about the full vacuum. And the full vacuum is different than a regular vacuum. It does more stuff. And so first we'll talk about this limitation of a regular vacuum, and then we'll talk about why you might want to do a full vacuum to fix that limitation. So on the left-hand side over here, we have a table that has 3 pages listed out. So it's sort of this combination of zoomed in and zoomed out view now that there's 3 pages, one after the other. This blue part, this page header, tells us where exactly the new page, one new page starts from the next. And each one of these pages has 6 tuples that have been added into that page at different points. And the way it's drawn, there is no free space inside of any of these pages. If we perform a vacuum, then the vacuum process happens only on a page-by-page basis. So each one of these pages has 5 dead tuples, 5 dead tuples, 5 dead tuples, and the vacuum process will remove those dead tuples and give us more free space over here so that we now have more space to insert new tuples. On the right-hand side over here, if I were to run an insert command, I would have a lot of free space. Postgres will decide based on its own heuristics which one of these pages to insert the new information inside of. But I will not have to create a new page to insert anything. On the left-hand side, because there's no free space anywhere, if I were to run another insert or even run another update, I would have to add a new page that would then take up more disk space. So the vacuum makes future updates and future inserts more efficient, not having to create new pages. But the vacuum process will never give you back more free space than you started with. If you're running out of disk space on your machine, for example, maybe you have 10 terabytes available and your database is currently at 9.9 terabytes, so you need to make up more disk space. Running a vacuum process will not help you, even if your entire database is full of dead tuples, because it happens only on a page-by-page basis. On the right-hand side over here, though, we can see that there would be plenty of room to combine these tuples together, combine these pages into one smaller table that contains only 1 page instead of 3 semi-empty pages. And that is what the full vacuum does. So this diagram over here illustrates what goes on inside of a full vacuum process. On the left-hand side over here, we have the same starting table that has many dead tuples. And then in a full vacuum, it starts by creating an entirely new table in the database that is empty. And then walking through the left-hand table over here, 1 page at a time, inserting all of the tuples just one at a time into this new table over here on the right-hand side. And so at the end, you end up with sort of compressing this 3 pages down into 1 page over here. And then you can delete this old file once you're done with it. So the full vacuum is able to actually free up disk space, whereas the regular vacuum is not able to do that. This seems like, okay, it might be always a better thing to do then, but the disadvantage of the full vacuum is that because you're going over this and restructuring everything, this cannot be done concurrently with, say, like inserts or updates or even select commands. So the full vacuum acquires an exclusive lock on the table. Nothing else can happen during a full vacuum, but the regular vacuum, also sometimes called a concurrent vacuum, because the regular vacuum acquires only a share lock, which allows selects, updates, and inserts, a lot of other things to go on at the same time, and so much more friendly in that sense for like a database that's actually running in production. If you're a company like Instagram, have a lot of real-time users connecting at every hour of the day, then you would only ever want to have your database running this concurrent style of vacuum and never running a full vacuum, because the full vacuum would bring your website down while the full vacuum runs. If you've ever used a website that has like a maintenance schedule, like once a month that's down for an hour sometime at midnight over the weekend, one of the causes of that is a database that needs to have a full vacuum performed on it at a regular interval, because nothing else can happen during the full vacuum. Yeah, that's any questions about the difference between the regular vacuum or the full vacuum? Okay. Then one last big picture concept for us to talk about, give you a high level overview of, and that is this idea of a visibility map. What is a visibility map? Inside of the Postgres database, we said that there is a file for each table, and it turns out that there are several auxiliary files as well, helper files. One of those helper files is a visibility map. And the visibility map is useful in many ways for speeding up many different operations inside of Postgres. In this case, it's just talking about how to speed up the vacuum operation. But again, we'll talk later on about how it's also speeding up the select operations. The visibility map has one entry for every page in the database. And that entry is either a 0 or a 1. It is a 0 if the page contains a dead tuple. So this page right here contains a dead tuple right here. And it is a 1 if that page does not contain a dead tuple. So ideally, we would like our pages inside of our table to have as few dead tuples as possible, to be as efficient as possible. And so we would like our visibility map over here to have as many 1s inside of it as possible. When the vacuum process, so the origin of the visibility map, why it was originally added to Postgres is to speed up the vacuum process so that the vacuum process only has to look at those pages where the visibility map is set to 0, and because it has a dead tuple inside of it, and it can skip these other pages. So that's the origin of the visibility map. That's the only thing they'll talk about it in terms of this chapter right here. But we would like our visibility map to basically always be as many 1s as possible. And there's a process in Postgres called auto vacuum that sort of automatically vacuums tables. And it's normally set so that when around 80% of these values become non-1, then it will do the vacuum and restore 1s over here, make as many pages as possible without dead tuples inside of them. Any questions about the visibility map, why it's important? Okay. I realized the material for today was all, I don't know, boring's not the right word, but different than the other classes, maybe harder to follow along with, harder to be engaged with, harder to see exactly how you're going to be tested on these things. But again, recommend that you read through these sections, focus on making sure that you understand each of these images and why they're important. How you'll be tested on this. Again, you'll have the quiz that will follow those just true or false questions. And on the final exam, I will just ask you essentially to draw me some of these diagrams related to whatever database it is that you're talking about and explain to me the performance implications of those diagrams. I think we can stop for today, though. We'll stop a little bit early. Question, yes. For the quiz, the only limitation for the quiz will be you can't communicate with another student. You'll be allowed to use your computer, whatever handwritten notes you would like. The main idea of using the computer is that you would be able to reference these documentation and actually look up the information. So the way to prepare for the quiz is to make sure you don't have to have everything fully memorized, but you at least have to know where to look to find the information that you need. Good question. Yes?
No quiz this Thursday?
And question is no quiz this Thursday. That's correct. The only thing this Thursday is your homework assignment due this Thursday. We'll have the lab on Friday, and then the quiz will be next week. If anybody has more questions about anything, I'll stick around and get those answered. Otherwise, we're done for today.